Hello everyone, Aaron here and welcome back to Leetcode. Today we are doing the snakes and ladders problem. Given an n by n integer matrix board where the cells are labelled 1 to n squared in a Boustrophedonning style, starting from the bottom left of the board and alternating direction each row. Boustrophedon is a Greek word. When the very ancient Greek used to actually write left to right, then right to left, then left to right, then right to left. So that's exactly what we're doing here. We're going left to right, then right to left, then left to right, and right to left. You start at square one of the board. In each move, starting from the square current, you can do the following. Choose a destination square next with a label in the range current plus 1 to the minimum of current plus 6 to n squared. So you can take between 1 and 6 steps forward, but you can't walk off the end of the board. This choice simulates the result of a standard. Okay, yeah. So you roll the dice. You can move some steps forward. If next has a snake or ladder, you must move to the destination of that snake or ladder. Otherwise, you move to next. The game ends when you reach the square n squared. A board square on row R and column C has a snake or ladder if board RC is not -1. The destination of that snake or ladder is board RC. Squares 1 and n squared do not have a snake or ladder. Note that you only take a snake or ladder at most once per move. If the destination to a snake or ladder is the start of another snake or ladder, you do not follow the subsequent snake or ladder. For example, suppose the board is -1, 4, or -1, 3, and on the first move your destination square is 2, so that would be this 3. It says we move to position 3, which is this. Oh, sorry, yeah, it's this one here because we're moving in a slightly funky direction. This moves up to here, but we do not follow the subsequent ladder to 4. Return the least number of moves required to reach the square n squared. If it is not possible to reach the square, return -1. Okay. Lots of funkiness going on here. We start here. We want to jump up. We want to move forward. We want to jump up. We want to move across. So we can do this in 1, 2, 3. No, sorry. 1, 2, 3 moves. Is that correct? 1, 2, 3. Why is that not? You start at square 1. 2, don't. Oh, that's backwards, sorry. Do, don't. Yeah, so 1, 2, 3, 4. Yes, I can't go 15 to 14. I can go 14 to 15 though. Okay, that makes sense. Right. My immediate thinking is this is a graph search problem, and it's a fairly straightforward one. It's a breadth first search problem because we're looking for the shortest path. What we want to do is basically we need to do a breadth first search. Now, I've coded up breadth first search a few times on this channel, but we'll go through it again. I'm going to need the collections library from Python because breadth first search is all about having a queue, and it's a queue of different paths we are exploring. So the queue is going to be a collections.deck, I think it is, and it's going to start with position 1 on it. And that's going to be the only thing there. And the way this works is while there's something on the queue, I forgot the API for this. I think it's pop left, or is it just pop left? I think it's got the underscore, I'm not sure. So we want to also maintain a set of visited things. So while there's something on the queue, take one thing off the queue. Now, because we're using a queue, we know the first thing that we're going to take off was the first thing that we put on. And that means because we're exploring these in a frontier manner, the first thing to come off is going to be the shortest thing so far, where every step is of cost 1. And that's perfectly true here. The trick is going to be if path -1 is equal to len board squared. So this is a 6x6 board, for example. So this is, if we're at our final destination, return the length of the path that we took, -1. Because if there's 4 states that we visited, we visited 1, we visited 15, we visited 13, we visited 35, and we visited 36. So that was 1, 2, 3, 4, 5 places we visited. That was 4 hops to navigate between those 5 positions. Otherwise, what we want to do is we want to say visited if path -1 in visited continue. We've already been here. We don't need to try again. Visited.add path -1. Now actually remember to write down that we've been where we are. And then for step in self.neighbors of path -1. What we want to do is we want to look at all the places we can go. So if I'm at 1, I can go to 2, 3, 4, 5, 6, or 7. I can go to any of those spots. So I want to effectively try them all. Q.append path plus the step. Extend our path that we're exploring by that 1 step. And if we get nowhere, we need to return -1. So if for some reason it's impossible to finish the game, you'd hope not, but someone might have built a terrible board where you just get stuck in a loop of snakes or something. I don't know. There's just snakes all the way leading up to the end. Maybe. I don't know. Anyway, so this is effectively solved now with one. I don't need to make this self.neighbors. It can just be neighbors. With one little complication, which is this make neighbors. That is this problem, effectively. A standard breadth first search with a custom neighbors function. So let's make a dictionary. And initially it's going to be I goes to the empty list for I in range 1 len board squared plus 1. So this is a 6x6, so that's 36. So we want them all to be in the range 1 to 36. Initially they can go nowhere. For I in range, for I in neighbors.keys, so for every node, what we want to do is for jump in range 1, 6 plus 1, effectively. In fact, let's just do this. Final square is len board squared. Now, we need to be a little bit careful here. If I plus jump if I try and index, the board at position I plus jump, and it's a -1. Neighbors I dot append I plus jump. In fact, no, hang on. Next is going to be I plus jump. Don't quite like using next because it's a keyword in Python, but it matches the problem description quite well. Let's call I car because it's effectively what it is. So if next is greater than final square, continue. We can't do anything. We simply can't get there. In fact, I'm going to change this slightly. I'm going to make this next be car plus 1. The min of car plus 6 final square plus 1. So that now effectively matches this statement here. Again, that's nice. I like it when that happens. If next is beyond the final square, well, it can't be now. So that all simplifies away. If the index is -1, it's a regular square. That's great. Else neighbors car dot append. Let's call this target actually, because I don't know how expensive this function is going to be. Haven't written it yet. So if we're jumping to a regular square, just jump straight to it. But if we're jumping to a snake or a ladder, we have to have followed it. But we don't want to recursively follow it, so we're just going to go to the target and count that as the next step we're on. One thing that's slightly unclear. Can I so my question is, if I landed on, say this 2 actually pointed to this 14 and starts a new ladder, can I in the next move choose to follow the ladder? I don't think I can, because I have to move away from where I currently am. So I don't think I can chain them at all, in fact. So that's interesting. Anyway. That's effectively the loop I need to do to determine the neighbors. It's just this index business. How do I actually compute the index of the board to get the position? Well, let's define that. If the index of self board idx. Oops, I've got a self up here. Ooh, that's a good question. So if I'm given n is len board, so index -1 mod n is going to be my distance from either the left or the right. Index -1 divided by n, that's going to be my row. So if this is 36, we turn that into 35. 35 divided by 6 is 5. Ooh, no, I want to do this the other way round, don't I? So here, for example, this is 1. This is going to turn to a 0. 0 divided by 6 is 0. but I want that to say 0, 1, 2, 3, 4, 5. N minus 1 minus that. So hang on, if we had 6, that's 6 minus 1 is 5 over 6 is 0. 6 minus 1 is 5 minus 0 is 5. 0, 1, 2, 3, 4, 5. Good. If we were at 25, that's going to be 24. 6, 4 is 20, so it's 4. 6 minus 1 is 5 minus 4 is 1, so 0, 1. Perfect. So the column now is equal to, if row mod 2 is equal to, if it's an even row, which way am I going? Well, I always start going that way. But the problem is whether that's even or odd is equal to n mod 2. So basically my question is, if I'm in this bottom row here, I want to just use the offset. Otherwise, I want to do n minus the offset, I think. That's a bit of a mess, that one. Let's do some printing. Neighbors is not defined. List index out of range. Okay. 6. So it's a 6 by 6. I'm looking at offset 5. Oh, hang on, I didn't print the index. That would have helped, wouldn't it? I'm looking for index 12, that one there. So it should be an offset of 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, I see. N minus offset minus 1. There, I had an off by 1 error, didn't I? It's the same as up here, actually. N minus 1 minus offset. The reason I had this offset was I was saying, well, 0, 1, 2, 3, 4, 5, it's sort of 5 off from the side, but it's off from the other side. And if it's a 6 wide row and it's 5 off, that should actually get me back to 0, which is a mess. A huge mess. Anyway, I'm happy with that. So let's comment that out. Collections, it's because this particular class is lowercase for reasons I will never understand. And that doesn't have an underscore, again, for reasons I will never understand. Python, I love your collections module, but oh my god, nothing is consistently named. Okay, how did this get somewhere? Show me the neighbors. I'm worried about the neighbors. So we've said 1 can get to 2, 3, 4. Ooh, it shouldn't be able to get to 2. So the indexing is bad. The indexing is bad. Turn that back on, please. 0, 1, 2, 3, 4, 5, 1. So for indexing 2, we should have got 5, 1. Have I got these the wrong way around? I do. I have them the wrong way around. Okay. Oh, of course, because it's n minus 1 again that I should have been checking, not n. Anyway, that works too. Let's, just for my own sanity, let's turn that into an n minus 1. So if we reach the end, that's the first row. Oops, can't highlight that. If that's the first row. That's n minus 1. That's the row we're on, so we're heading the right way. Otherwise, we're heading the wrong way. Oh my goodness, this Boustrophedonning reading is melting my brain slightly. I knew the indexing would be the trick with this problem, and it's certainly proving to be. Right, now let's see. Oh, I'm still printing neighbors. I'm not going to be printing neighbors. Whoops, well, we were fast enough anyway. We beat nothing. Probably not helped by having this extra print left inside it. You could also possibly be more efficient in how you traverse the grid, although just removing that print helped us substantially. Excellent. Another improvement would be to compute the neighbors dynamically rather than compute them all up front, because we never go back and check any of these things. So that's probably very wasteful in the memory department, but in general I'm happy with this. This is almost certainly the standard solution. I don't think there's anything creative about this solution. I'm going to sound like Matt Levine, but rather than fraud, it's going to be everything is a graph search. It's because everything is a graph search if you squint hard enough. So yeah, I'm happy with this solution. It's a breadth first search, just being careful in how we define neighbors. I like the composition of this. Yeah, happy. Do let me know how you did it. Did you manage to get a bit faster than I did? Apparently a lot of people got a lot faster than I did. So how did you do it? Obviously you did something a little more specialized to this problem that you could do. Do let me know down in the comments. Do like, comment, subscribe, all of that good stuff. I do read every comment. And I appreciate every like that these videos get. So thank you very much, and I will see you next time. Bye.